All right. Hey, so we are looking at acceleration in 1 and 2 dimensions. So first example here is we're going to be using for these questions many of the kinematic equations that we developed in the previous video. And so we got a motorcyclist that's traveling initially at 12 meters per second west, changes gears and speeds up for 3.5 seconds, during which time he has a constant acceleration of 5 meters per second squared. So that means that each second he accelerates at his velocity will become 5 meters per second, a little bit more than that, more greater, larger. Okay, for a total of 3.5 seconds. What is the motorcyclist's displacement during this time interval? Okay, so you can kind of think of this as a graph, where you've got a velocity, some sort of initial velocity of 12, and then 3.5 seconds later, you have some other initial velocity of, or some unknown final velocity. Okay. Now, what you can do is you can multiply 3.5 times this to figure out how much more we need to add to the velocity. And then you can end up figuring out the area under this curve, which would end up being the total displacement. Okay. But in the end, we have a series of formulas that end up giving us all of this. Rather than doing this graphically, we can actually just use one of the 5 kinematic equations. All right, so what I want to do here is I'm going to write down what we're given. Initial velocity is 12 meters per second. That's a vector, and that's west. And we've got a acceleration, also a vector, of 5.1 meters per second, and that's west. We've got a time of 3.5 seconds, and we're looking for a change in position. All right, now if I consult the chart or my formula sheet, I'll discover that I end up having this formula here. Displacement is equal to initial velocity times change in time plus half of the acceleration times the square of the time. Okay. Now, why would I choose this formula? Well, because it has 3 of the things. It has what I'm looking for, first of all, which is the displacement. And the rest of the stuff in the formula that I'm just written down, I know all of that stuff. And so effectively, this in physics, the whole goal generally is to choose the right formula. Many of the questions are just solved by choosing the correct formula. And so the basic gist of choosing the correct formula is to look at what you are trying to find and then look at all the information that you already know and then choose a formula that's full of that stuff. Okay. And so there it is. I've done that. So I'm going to go ahead and find my displacement, right? So I'll take my initial velocity. So it's 12 meters per second west. Okay. Times time of 3.5. Okay. So this is multiplied by 3.5 plus half of my westerly acceleration times my time squared. So this is 5.1. I tend to not put, I know I might get yelled at by a lot of people, but when I plug in to formulas, if I'm very organized, I can avoid putting units everywhere, right? What I don't want to avoid writing are the directions. Those are going to be important. Okay. Um, but if I end up putting units everywhere, I can do that. That's not going to be an issue. But it tends to take up a lot of space. And then as I'm plugging things into my calculator or solving for this information, my eyes kind of get, I don't know, just after lots and lots of hours of doing this stuff, your eyes get a little tired of looking at units and things like that. So I kind of just put the numbers in. As long as I've got my units written over here clearly in my givens, in my opinion, this is okay. Now, other teachers might say, well, no, you have to write your units down at all the time. And so, well, basically, you want to just sort of figure out what your teacher sort of prefers. Anyway, once you plug all this stuff in to a calculator, you end up getting 73, right? So delta D is, oops, I already had this worked out prior to. I didn't want to have you guys sit and watch me plug stuff into a calculator. And meters. Why do I know it's meters? Well, because I know the kinematic equations have what's called unit agreement, meaning that if I take a velocity and I multiply it by a time, this is going to be a meter. So velocity meters per second times time, the seconds cancel, this is meters. And acceleration has a meters per second squared on the bottom. I multiply it by seconds squared, and I'm left with a meters. A meters plus a meters is a meters. And so I just know that my kinematic equations are going to be appropriate, okay? Now, this is a one-dimensional situation because both of my vectors are west. So my final direction is just going to maintain that westerly direction there, okay? So during this whole time, it's 73 meters that he went. And if you were to figure this out graphically, you would see that the displacement here, oh, that was the most ridiculous 73 I've ever written in my life. This is 73 meters in this area, the area of this thing, okay? We could figure out our final velocity as well. We weren't asked to, so we'll move on to the next example question, okay? Here's one. We got a rocket launched vertically from rest, and it reaches a velocity of 6.3 times 10 to the 2 meters per second up. So it's 630 meters per second, okay? This is an altitude of 4,700 meters. I just automatically converted this into meters. Why do I do that? Because my velocity is in meters, and I don't want to mix kilometers with meters in my formulas. Otherwise, I'll be, 10 times off in my answers or even things like that. So, well, not exactly 10 times off, but I'll be off. My answers will be not correct. Because, if I can't add a meter with a kilometer, whatever, without converting them both to meters or both kilometers. General rule of thumb is to go into meters. Anyway, determine the rocket's acceleration during this time. Assume that it is constant. So our acceleration is constant in this question, and so I'm going to look for it, my acceleration. That's what I want to find. My velocity final appears to be 630 meters per second. My change in position was 4,700 meters. And there's only two other things. I could have a time, which I don't know, or I can have an initial velocity, which it doesn't appear to give me either. But because it says that it starts from rest, I can then assume that my initial velocity is 0 meters per second. So this is a key thing you want to keep in mind during many physics tests and homework exercises. When you see the keyword that it's things start from rest or come to a stop, for example, that's going to give you indication that your initial or final velocities can be assumed to be 0. Anyway, so now if I sort of, again, decide, well, which formula do I want to use? So what I'm trying to find is acceleration. I have a final velocity, I have an initial velocity, and I have a change in position. So, I think if you consult your formula sheet, or if you recall your kinematic equations, the most appropriate one to use in this case is going to be this one here. Okay, so let's see here. So let's see, what do I want to find? I want to find acceleration. There it is. Well, in the previous example, the displacement, or the change in position here, was already isolated. So this was quite simple. In this one here, my acceleration is not isolated. It's sitting there. So I'm going to have to do a little bit of algebraic work and pass over this initial velocity, this 2, and this delta d here, okay? So it's going to be velocity final squared minus initial velocity squared is equal to 2a delta d. And basically, what we're looking at now is I'm going to have to divide by the 2 and divide by the delta d. And so I'll get this, okay, 2 and delta d. And this is acceleration. And notice I did not write my vector symbols, because if you recall, when we developed this formula here, we omitted the vector symbols because of that concept of multiplication of vectors. And then what I told you is, if we use this formula, what we will likely end up doing is deciding the final direction of my final answer based on the context of the question. Okay, so if I go ahead and put these values in, I've got 630 squared minus 0 squared over 2 delta d, which is 4,700 meters. And this is going to give me my acceleration. Notice I did not put any directions in here, okay? And so I end up with my acceleration of, I just went ahead and moved it. I'm going to switch this over to this side after we do all of this calculation, is 42 meters per second squared. And now we have to decide on I'm going to get rid of that vector symbol, because it's not until here that I'm actually making it into a vector. Now, based on the context of this question, it started from rest, its final velocity was up, and it had a constant a constant acceleration. So if it started from rest and the end it was going up, I'm going to go ahead and just say that my direction is up. Okay, is up. All right. And that's what I mean by, you just basically have to look at the context of the question to determine this velocity. Okay, sorry, this acceleration. Later, we'll use this formula, and you'll see that these velocities might have a negative version and a positive version, because when for example, if I solve for final velocity, I'd have to square root this, okay? Which means I'd have a plus or a minus in front of this, because remember, the whole thing of square rooting a square asks you to put a plus or a minus on the other side of the formula. And based on that, you'll have two possible solutions, a plus or a minus, okay? Let me develop this. So let's say I were to try and solve for my final velocity. If, for example, I had a different question where I was given acceleration, initial velocity, and a change in position. Well, there's my initial velocity. So I would add my 2 times my acceleration times my change in position. And then I would square root the whole thing. Well, remembering that square rooting gives me this whole idea of a plus or a minus, which means I would have actually two possible velocities, one up or down, or left and right, or north and south, depending on what a positive velocity meant in the context of your question. And then, based on the context of the question and further, you would have to choose which is the most appropriate value for the context of the question. Would it be more appropriate to have a final velocity that's up or down in that situation, for example? We'll talk about those throughout the semester as well. So here we've got a curling rock that's sliding on ice, and it undergoes a constant acceleration of 5.1 centimeters squared east as it travels 28 meters west from its original position before coming to a rest. Oh, here we go, coming to a rest. Determine the initial velocity and the time of travel. So it looks like we have two things to do here. By the way, a curling rock is this thing. I don't know, it's an Olympic sport, I believe, where you kind of take this sort of heavy stone and you throw it slowly in an attempt to get it into a target of some sort. And you've got some friends of yours that are like skating in front of it, and they can like brush the ice with like brooms and things like that to make it turn in particular directions or slow down or speed up or whatnot. So I don't know. But let's say this is a constant acceleration. So it's just basically decelerating here. And you don't have any friends with brooms in this particular example who can change the direction of it. So this is a very simplified situation where you're doing this. So anyway, it comes to a rest. All right. So let's analyze this question, see what's going on here. Well, again, as you can kind of start gathering, what I tend to do in these questions is I write down my givens, okay, and the things that I could potentially search for in a kinematic equation situation, okay? So I've got delta t, that's my time. It turns out I'm actually looking for that. I've got my delta d, which is 28 meters west. I've got my final velocity, which is 0, because it comes to a rest. Okay, so I'm going to start writing this down. 28 meters west. My final velocity is 0. My initial velocity was given. Was it not given? No, I actually need to find the initial velocity. But the acceleration was given. It's 5.1 east. So I'm gonna change this into meters per second. So instead of using 5.1, I'm going to use 0.051. So 0.051 meters per second, and that's going to be east. Okay. And yeah, that's pretty much what we're looking for. I've got an acceleration, I'm going to find my time, and I'm going to find my initial velocity. So let's check this out here. All right, so to find my initial velocity, I'll go ahead and use the above formula, this one up here, right here, knowing that I have my final velocity, my acceleration, and my change in position. Okay, so I'm going to write that down. So final velocity squared equals initial velocity squared plus 2a delta d. Now, to solve for initial velocity, I'll subtract this stuff over to that side. And so I've got final velocity squared minus 2a delta d equals initial velocity squared. And I'll square root that side, noting that I will put a plus or a minus in front of it. So now if I go ahead and plug this information in here, I've got final velocity squared, and then I've got 2a delta d. Interesting. Well, I've got one of these. Notice that my delta d is west, and my acceleration is east, which effectively means one of these two things need to be negative, and the other one needs to be positive. So I'll go ahead and say, well, was there, let's see, direction. Here in the diagram, they've already told us that this is the positive direction. So therefore, west is positive, which effectively means that the acceleration could be considered to be negative because it's actually pointed not in the positive direction, but the negative direction. So my final answer here is going to be plus or minus. Ooh, that's a bit tricky there. Plus or minus the square root of 0 squared minus 2 times a negative 0.051, that's my acceleration, times a displacement of 28, and I'll leave that guy positive. And this is my initial velocity, which I won't put a vector symbol on for the time being. And note that this is awesome because I had a square root here, and this negative here effectively help me out and cancel each other out, which is amazing. And so the final answer is going to be plus or minus the square root of whatever this thing is, which is a positive value, or plus or minus 1.7. The square root of whatever's in here turns out to be 1.7. Okay, so it's plus or minus 1.7 meters per second. Okay, and that's my initial velocity. Okay, now the question arises, was that was it plus or was it minus? Both are valid answers in this mathematically. But in the context of the question, notice my initial velocity was in the positive direction. So I'm going to choose the positive value, and then I will effectively be allowed to designate this as being a vector and saying that it goes to the west. And then I want to cancel out my plus or minus and only use the plus. So therefore, my initial velocity is 1.7 meters per second west. Okay, that's A. Now, if I go ahead and I try and solve for B, okay, let's see, what am I trying to find in B? The time. Okay, well, in order to find the time, note I have everything, but a really easy formula to use is acceleration is equal to final velocity minus initial velocity over time. Solving for time is final velocity minus initial velocity over acceleration, right? So this looks a little it looks a little tight. I don't like how I wrote that. I'll explain this a little bit better. So algebraically, this time can be multiplied over to here, and this acceleration then can be divided over to here, okay? Or effectively, what you do is you multiply both sides of the equation by time over acceleration. So time over acceleration. That way, these two accelerations cancel, leaving just a time. And then these two times cancel, leaving just an acceleration on the bottom. Okay? And so what's left on the right side of the formula, right here, is a final velocity minus initial velocity divided by an acceleration. So you're going to want to get familiar with this algebra so that you can quickly do that. What I oftentimes tell students is when you get into physics, there are so many formulas that are a number or some concept equivalent that's set equal to a ratio. What you want to just sort of start getting comfortable doing is being able to take this number and switch their positions, because algebraically you can go ahead and do that, but without having to write it out every time, because you want it to sort of start to become a second nature type move. This allows us to get our time, okay? And so now I've got a final velocity minus an initial velocity divided by an acceleration. So what was my final velocity? 0. Cool. So 0 minus my initial velocity of 1.7. That was positive, remember? It wasn't negative because it was a positive west, because it was in the positive direction, divided by my acceleration. And remember, my acceleration is negative because it's east in the non-positive direction, okay? So that means my negative 0.051, okay? And this makes sense because these two negatives will cancel, allowing me to have a positive value for my time elapsed, which is 33 seconds, because it's 1.7 meters per second divided by a negative 0.051 meters per second squared here, okay? So this was a situation where there was a lot of interesting details that occurred. First of all, we had to deal with the fact that this formula here has no vectors in it, and that when I square root a square, I automatically get a plus or a minus on the other side, along with the square root, forcing us to, in the end of the question, choose whether or not plus or minus is the most appropriate answer. Then, over here, I had to keep track of the fact that my direction is positive in this direction. So this is the positive direction, meaning all vectors facing that way should be positive. All vectors facing the other way should be negative. And notice my acceleration is negative. So therefore, that way, when I place it into this formula over here, that negative comes out, and which is a nice thing, because then it allows me to cancel the above negative, giving me the appropriate time. Very important details to keep track of in questions like these. Okay, so that's acceleration in one. Oh, no, this is just one dimension. Sorry, let me cancel this out. One dimension.